Hello from Arrikto. This video is a summary of the demo that was presented at VMworld 2016 in Las Vegas. In this video, we are going to demonstrate how to move thin snapshots around the globe. For the purposes of this demo, we simulate three distinct data centers in Ireland, Seattle and the Bay Area, each one with a distinct VMware deployment, backed by its own storage. On DC1 in Ireland, we start with a golden image, and we spawn 256 distinct VMs out of it, each one with its own independent virtual disk. We visualize this with a 16x16 matrix, where every cell represents a single VM, and the cell color represents the state of the VM. We then snapshot the VM's virtual disks, based on admin-defined policies, and move them intelligently across locations. Thus, the snapshots will fly across the ocean, and they will eventually reach DC2 in Seattle. There we spawn another 256 VMs. So let's have a look at these two data centers. On the upper right and upper left side, we see the matrices for DC1 and DC2 respectively. Below each data center, we have a vSphere client connected to vCenter. On both data centers, vCenter manages a bunch of ESXi hosts, and currently there are no VMs running. We use our trusty script to coordinate the whole procedure. First of all, we present our golden image on DC1. If we navigate into vCenter data stores on DC1, we can find our Rockvival data store. Inside lies our golden image. Now we create 256 clones of the original golden image, visible as VMDKs in the Rock data store. Then we create 256 VMs using those VMDKs and power them on. Every time a VM is powered on, the corresponding cell changes its initial grey color. Here we see the final picture, where all the VMs have the same white state, which denotes that the VMs are up and running. The whole process took us only 74 seconds to clone the original golden image to 256 virtual disks and create 256 VMs. If we pick a color and draw one cell, the respective VM receives a request to modify its own disk state. We use those colors just as a trivial representation of a stateful application that persists something on disk. For the purposes of this demo, we have already created a picture. We load it and now all the VMs have an updated state. Let's now switch to the vCenter of DC2. We can see that Rockvival is empty, and there are no VMs running. Thus our matrix is also empty. In the meantime, our globally distributed registry is set up and syncing the snapshots of the disks from DC1 to DC2, ensuring that they will find their way from Ireland to Seattle. We can see the syncing progress in our script. If we refresh Rockvival on DC2, we can see that it is now filling up with VMDKs. Every VMDK is 10 GB in size, so we're talking about 2.5 TB in total. How long would you expect to take this amount of data to cross the Atlantic? With a gigabit Ethernet link, it would take more than 5 hours. And we can see that it took only 40 seconds to transfer all the disks and 37 seconds to present them as VMDKs. We have reduced syncing time from approximately 5 hours to 40 seconds by just transferring only the data that has changed since the VMs have been created. So moving on to DC2, we are going to spawn another 256 VMs there, this time from the set of images that just arrived on DC2. These images already have state, so they won't come up white. We expect the left-hand picture to look exactly the same as the right-hand picture. And this is what happened. The whole state has been transferred intact. We can still draw the picture the way we like and consequently change the state of our random VM. Okay, so this may look nice, and it is, but how is it different from just replicating from one location to another? This is not just a backup DR solution between two locations, so to make things more interesting, let's put a third data center, say in the Bay Area, in the mix. This DC has a vCenter up and running, managing again a number of ESXi servers. Currently there are no VMs running. In a real-life scenario, people would continue working in DC1, modifying their VMs. As a result, a new version of each image would be created. To simulate this, we'll load a new picture onto the matrix for DC1. All the VMs move to a new state, which is synchronized to disk and will eventually find its way to a new version of the corresponding image. Again, our handy script will coordinate the procedure. What's been going on in the background is that these new images are being transferred, again thinly, to DC3. The thing is, DC3 is pretty close to DC2. How much data is that actually needs to cross the Atlantic now? Here is the real interesting part. Our data centers form a peer-to-peer network and they transfer data among them, so DC3 will find the needed parts of the original drawing, which have remained unchanged, right from DC2. So the data transfer load is automatically balanced between the two links, the shorter, probably faster link connecting DC3 and DC2, and the longer cross-Atlantic link connecting DC3 and DC1. If we refresh RockVivol in DC3, we can see that it is now filling up with VM decays. This time the procedure took us only 26 seconds to synchronize the images. As we can see, there is a significant time decrease. The reason is that DC3 is connected with two peers, DC1 and DC2. The images have arrived on DC3. We can now start the VMs. Again, we have presented those images as writable clones, so we have to create one VM per image and power it on. We expect the left-hand picture to look exactly the same as the right-hand picture. And yes, it is our updated drawing, showing that VMs on DC3 have been spawned and are in the proper state. Now let's have a look under the hood. How did all this happen? Let's look at a single data center. We have some sort of persistent storage and the virtualization platform, in our case VMware, on which we run our VMs. Our software sits between the persistent storage and the platform, implementing a set of intelligent data services, independent of the underlying storage technology. This includes our thin clone snapshot data service that we have seen in action. To control the data services layer, we use our distinct gateway service. The gateway sits along the rest of the data services and exposes an HTTP interface to the user, so we use the gateway to manage our images. Let's take a look at the gateway of DC3. It looks similar to a file storage service. It doesn't actually store physical files, but rather underlying virtual resources, along with associated metadata. Entries in the gateway are organized in buckets and are versioned. There is one bucket in DC3 that contains 257 images, our original golden image plus our new 256 images. Notice the green downward pointing arrow on the bucket. This bucket contains images being synchronized P2P from another DC, in this case DC1 and DC2. If we open the bucket info panel, we can see the peers that we are getting the data from, as well as the bucket reference that it is subscribed to. Now let's have a look at the gateway on DC1. This is our single published bucket, signified by the upward pointing arrow. If we go into the image list and click on an image, we can see all the different versions of it. Don't forget that during our demo, due to the admin-defined backup policies that we already mentioned, more than one snapshot of each disk was created. So this is why we see two versions. But where are these bucket references coming from? Well, we have created a global meeting point to find bucket references. We call this the indexer. The indexer also lets its gateway discover other gateways exchanging data for a specific reference. Using the search bar, you can search for buckets, users, and organizations. Let's navigate to our profile. It seems we even have some references here. Let's get one. We get the link and go to the gateway of Data Center 3. We are about to create a bucket and subscribe it to the link we just got. We provide our bucket with a name and then subscribe the bucket to the indexer link. Okay, so what is happening now is that our new bucket automatically fetches data, in our case a new set of Docker images. Now we are going to present this Docker image as a VMDK and start a VM out of it. Here it is. We can see that DC3 Docker VM has been created and is up and running. Let's get a virtual console. So this image seems to have been created on Docker infrastructure and now runs on VMware. Let's now recap. We moved 256 VMs from DC1 to DC2 in just 40 seconds. Then we transferred those 256 VMs to a third data center in just 26 seconds. Finally, we fetched a Docker image to DC3 and ran it on the VMware platform. I hope you enjoyed the demo. Thanks for watching. Visit us on Arrikto.com and find out more.